Hello, Pre-Cal. Today we're going to be talking about how to convert between rectangular and polar form. So what we have here is we have the diagram illustrating what we're going to do. So the idea here is if I have a graph, right, and you know what? I feel like it's just easier just to do an example. So if I have a graph, for example, and this first one's nice and easy, but if I have 6 comma 90, right? If I was to graph this, that just means you turn 90 degrees and you go up 6. So this is 6 comma 90. So that lives right there. And if I wanted to convert this to coordinate form, I mean, one, you can just literally just visualize it, right? And you can easily see that if I go up 6, right, and I didn't move x anywhere, this is the same thing as 0 comma 6. Easy enough, right? So just by drawing a picture, you can easily visualize it. But it can get more interesting, thank goodness. And what about something like this? So if I give you something like this, there we go. It's a little more interesting because this thing protrudes out. I guess I should do this in a different color. Let's say we'll do this in blue. All right. Okay, it protrudes out 60 degrees, and this is 4. So what could I do to figure out the coordinates? Well, you can clearly, easily draw a right triangle, right? You can easily make a right triangle, and you could solve for this, right? And what I would do is that I realize it's 30, 60, 90. This is x root 3. This is x. And this is 2x, so we would solve. So I would say 4 equals 2x, so x is 2. And if x is 2, then this is just 2 square root 3, which means the y value is, the x value is 2, and the y value is 2 root 3. And bada bing, bada boom, we have the value. All right. And I think that's simple enough. So the question that emerges then is why are in these instructions they have all these notes? Well, it's because this can get more interesting, right? Let's be clear here. We're keeping these values nice and easy using numbers like 60 degrees, right? If I gave you 59 degrees, you would have a problem. So what we can say as well, what's equally as true is that if I draw a triangle, if I have a line protruding out, let's just do it like so. If I call this theta and I call this r, I can call this x and I can call this y. And what I can see is that if I say sine theta is y over r, or simply if I multiply both sides by r sine theta is y, right? And by the same argument, by the same exact argument, I can say cosine theta is x over r. And again, if I just multiply both sides by r cosine theta is x. So what we're saying is another way to determine this value is to say that, hey, this coordinate is just r cosine theta, comma, r sine theta. Okay. Now I'm not a big proponent of memorizing and regurgitating formulas, but awareness of what the formula is nice, right? So I think you should be able to just think about it and solve it, but you can also you solve it using this sort of formula. So what am I saying is that if instead I don't want to draw a picture, I just want to use this formula here, I can just simply say that, let's use this blue here. if the x value is just r cosine theta, I can say 4 times cosine 60 is going to give me x, and 4 times sine 60 is going to give me y. And then I can look at my unit circle, or I can look at this picture, which is cosine sine, right? And we can see that cosine 60, right? Well, I guess this is not quite a unit circle, but if we were to look at a unit circle, 60 would be here, and that would be what? That would be 1/2 square root 3 over 2. This would be cosine sine, so this would be 4 times 1/2, comma, 4 times square root 3 over 2. Oh, look at that there. Guess what happens? Oh, so interesting. 4 divided by 2 gives me 2. 4 divided by 2 gives me 2, and this is 2 root 3. These are supposed to be in parentheses as well. So we have the value there, and that's the way that most textbooks will drive it, but I like the idea of visualizing it with a picture and solving it. But to each their own. Whatever makes you happy is fine. I think what's most important is that you understand what you're doing. Okay, so let's look at another one. 10, 225. So I'm going to draw a lovely picture here because I think a picture is worth 1,000 words. And I know 225 is right here. I apparently like to use the same colors over and over again. Let me distinguish that's a purple. And I know this length is 10. I also know that if this entire angle is 225, a little trick here, if it ends in 5, that means the reference angle, remember that term, is just 45 degrees. Yippee. And now I can draw my right triangle, because that's what almost all of the math that we deal with tends to be about. And what can I do? Well, what is the ratio? It's x root 2. So if 10 is equal to x root 2, then all I need to do is, let's see if I can find another color here. I chose kind of the same color again. Go with a little more pinkish. Divide by root 2. And 10 over root 2. 10 over root 2 is x, or I can say 10 root 2 over 2, or just 5 root 2 is x, right? We can rationalize the denominator, multiply top and bottom by root 2. Maybe I should be visualizing that. And that gives me 10 root 2 over 2, which is 5 root 2, which means that this is 5 root 2, and that this is also 5 root 2, which means this coordinate is 5 root 2 and then 5 root 2. And this is where you turn to me and you say, but Mr. Anderson, position matters. And I would say you're absolutely right. This is in quadrant 3, where everything's negative. So these would be your coordinates. Okay? And there you have it. So you can pick, you could also have done it using r cosine theta and r sine theta, and it would have generated the same result. Okay. Now we're going to do the same thing, but it is in radians. So the idea is that you do have to make sure that you are very comfortable with the unit circle. And in this class, we are not, at this point, we're not going to emphasize, we're going to assume that you know these values on the unit circle. So pi would be all the way over here. Here we have living pi. And this distance is out. This distance is out, obviously 5. So this one should be pretty clear. It's -5, 0 as a coordinate, right? You're going 5 out to the left, basically. Cool beans. All right, now let's do the next one. So this one's at pi over 6, and pi over 6 would be here. And what I do, and this is a length of 2 root 3, what I do is I personally think, well, I know pi over 6 is just 30 degrees, so I'm just going to say 30 degrees because that's easier for me. And this is 30, 60, 90, and we know the 30, 60, 90 values are going, come on, there you go, are 2x x in x root 3. So I can say that x is root 3. If you're concerned, I am just solving this equation quickly in my head, taking 2x equals 2 root 3. This is going to give me root 3 is x. And then what's really interesting is if this value here is root 3, then here we have root 3 times root 3, which just gives me 3. Okay, so this tells me, let me redraw this picture because I got all this math all over the place. This point here, thus, is at 3, comma, root 3, right? 3, comma, root 3. And there's my answer. Okay? Again, if you want to, you can use sine and cosine. I feel like at the end of the day, if you're doing this without a calculator, drawing a picture and labeling is probably the easiest approach to it. Okay, 5 over 2 and 5 pi over 3. Okay, again, I would encourage you to memorize the unit circle if you don't have it already memorized. I know it's been a while. It's been some time, but that will help you out immensely. And so we know that this length is 5 over 2. I should be putting this on the outside. This is 5 over 2. We want to know what this reference angle is, right? So we know if we're at 5 pi over 3, this is just going to be 60 degrees. And same thing. We say, okay, this is going to be, oh, I don't know why I did that. Let's see here. We'll go with blue this time. This is 2x. This is x root 3, and this is x. So we can say 2x equals 5 over 2. So x is equal to 5 over 4. And this is 5 root 3 over 4. And again, you're like, cool deal, Mr. Anderson, but you need to pay attention. And I really do. I make mistakes with this all the time. I have to pay attention to where the line is going, right? It's going down, so it's negative. And there you have it. And there we have it. So that is how we go from polar to rectangular. I hope that makes sense, and I will see y'all in the next math video. Goodbye for now.